Single core. This is where PCs lived before the word multitasking meant anything real. Chips like the Intel Pentium 4 and Celeron D shipped with a single core, and from 2000 to around 2008, that was the entire mainstream desktop. You ran one task. The CPU handled it. When something else needed attention, it waited in line. Gaming in that era worked because games were built around that limitation. Quake 3, Counter-Strike 1.6, and early Call of Duty titles were all designed for single-threaded processors. The hardware and the software were speaking the same language. Today, that language is extinct. Windows 11 will not install on a single-core processor. Microsoft set dual-core as the minimum requirement. If you somehow force a modern OS onto a single-core machine and try to run anything, Chrome with 3 tabs open will pin the CPU at 100%. Gaming is not a conversation at this tier. It's a physical impossibility. The Pentium 4 had a clever trick on some models called hyperthreading, which made the chip appear to Windows as 2 logical processors. It helped. It did not solve the problem. A single-core CPU in 2026 is a museum artifact that somehow still boots. It belongs in a display case next to a floppy disk drive, not in anyone's PC build. Dual core. Chips like the Intel Pentium Gold G7400 and Celeron G6900 shipped with 2 cores, and back in 2016 that was acceptable. Web browsing, office work, YouTube, light indie games, nothing demanding. Today, running a modern game on 2 cores is not a budget compromise, it's a hardware conflict. Modern games split their workload across multiple threads simultaneously. Physics, AI behavior, asset streaming, game logic, audio processing. When you only have 2 cores, all of that competes for the same 2 lanes. The CPU maxes out before the GPU even gets the data it needs to draw a frame. You can install a brand new RTX 5070 in a 2-core system and it will sit at 40% utilization while the CPU screams at 100%. The graphics card is ready. The processor isn't delivering. Even lightweight esports games become inconsistent. Valorant will technically load, but run Discord at the same time, and the frame pacing falls apart. The average FPS might look fine on screen. What you'll actually feel is lurching, stuttering gameplay that no settings change will fix. If someone is selling you a PC with a 2-core processor in 2026, they're selling you a paperweight with a fan attached. This tier lives in office checkout kiosks, light browsing machines, and as a reminder of how far the floor has risen. Quad core. Between 2018 and 2021, 4 cores was the budget standard for gaming. Chips like the Core i3-10100F and Ryzen 3 3300X handled 1080p gaming solidly. You could run Fortnite, Rocket League, and older AAA titles at respectable frame rates without breaking your budget. For a lot of people, this was the CPU that made PC gaming affordable, but game engines assumed more headroom faster than anyone expected. Today, a 4-core CPU can still technically boot every major game. What it cannot do is run them without becoming the bottleneck. In games like Cyberpunk 2077, Baldur's Gate 3, or any open-world title running dense AI simulations, all 4 cores hit 100% usage and stay there. Your GPU drops to 50 or 60% utilization because the processor can't queue frames fast enough. Frame rates aren't just low, they're inconsistent in a way that settings cannot fix. Streaming while gaming? Not possible. The CPU handling the game is already maxed. Add an encoder on top of it and the whole thing collapses. Competitive esports titles at low settings still work. CS2 and Valorant stay playable when nothing else is running. But the moment a newer title pushes real CPU workloads, or the moment you try doing anything else simultaneously, you'll hit the ceiling immediately, and it's a hard ceiling. In 2026, 4 cores is the floor for gaming. Not a comfortable floor. A floor with serious cracks running through it. Hexa Core. Between 2020 and 2022, 6 cores hit the exact right balance for gaming. Chips like the Ryzen 5 5600, i5 12400F, and i5 13400F were some of the most recommended CPUs of their generation, and they have aged remarkably well. Unexpectedly well, honestly. At 1080p, 6 cores handles virtually everything in 2026. Esports games never stress it. AAA games maintain strong frame rates. CPU-intensive titles like Cyberpunk don't drag it to 100% the way they punish 4-core chips. This is where the real controversy lives. The PC building community spent years arguing that 6 cores would age badly by now. For pure gaming, it hasn't. Most modern games still don't meaningfully use more than 6 to 8 threads. The frame rate difference between a Ryzen 5 5600 and a 12-core Ryzen 9 5900X in gaming benchmarks is often under 5%. The wall shows up the moment you try to do more than one thing. Streaming while gaming, your encoder fights the game for CPU time. You'll drop frames in your stream well before you drop them in your game. Running a Blender render in the background, forget it. Content creation at this tier is manageable at 1080p and starts dragging at 4K. The processor is not the right tool for anyone doing serious media production. If gaming is all you do, 6 cores is still a legitimate build choice in 2026. It won't last another 4 or 5 years without pressure, but right now, it holds. Quick question, how many cores does your CPU have? Drop it in the comments. Octa Core. This is the gaming sweet spot, and the Ryzen 7 7800X3D made absolutely certain everyone knows it. Chips like the Ryzen 7 5800X3D, Ryzen 7 7800X3D, and Ryzen 7 7700X deliver everything any game running today will demand from a processor. Physics threads, AI threads, streaming threads, game logic, all of it fits comfortably. The CPU stops being the conversation entirely. In CPU-sensitive titles like Microsoft Flight Simulator 2024, Cities Skylines 2, and Cyberpunk at 1080p, where the processor is the actual bottleneck, 8 strong cores with high single-threaded performance pull ahead of everything. The 7800X3D's 96MB 3D V-cache kept it at or near the top of gaming benchmarks for 2 consecutive years, regularly outperforming chips with twice the core count in most games. One thing worth addressing directly, Intel's hybrid architecture complicates this tier. A Core i7-13700K has 16 total cores on paper, but 8 of those are efficiency cores built for background tasks, not the primary game thread. For gaming, what actually moves frame rates is performance core count and clock speed. A chip advertising a high total core count is not the same as one with 8 strong performance cores running at 5 GHz. Don't let the number fool you. For content creation, 8 cores works but shows its limits. 1080p and 1440p video editing runs smoothly. Complex Blender scenes and long 4K exports take patience. Streaming while gaming is fully manageable at this tier. The encoder runs, the game runs, and they don't compete for the same resources. For most gamers, 8 cores is the right answer. Everything above this is for people who need the CPU to do more than play games. 12 core. This is where gaming stops being the constraint and your workload becomes the new ceiling. Chips like the Ryzen 9 5900X, Ryzen 9 7900X, and Core i7 12700K sit at 12 cores, and at this point, no game in existence will push this processor anywhere near its limit. Multitasking stops being a concern. Gaming while streaming, recording gameplay, and running your full desktop setup at once, the CPU handles all of it without any task squeezing the others. Content creation at 12 cores is where work starts feeling genuinely fast. 4K video editing in Premiere Pro becomes noticeably more fluid. Blender render times drop compared to 8-core configurations. If you produce content alongside gaming, this tier removes the CPU from your list of problems. The honest trade-off: gaming alone will never justify this core count. The benchmark differences between a 12-core Ryzen 9 5900X and an 8-core Ryzen 7 5800X in most games land in single-digit percentages. You are spending meaningfully more money for frame rate gains you often cannot see. But if you stream at professional quality, edit videos for clients, or run heavy developer tools alongside gaming, 12 cores earns its cost quickly. 16 core. This is where gaming and serious professional work stop competing with each other. Chips like the Ryzen 9 7950X and Core i7 13700K sit at 16 cores, and the CPU effectively becomes the last thing you'll think about upgrading for years. For pure gaming, you will see no improvement over 8 cores. Zero meaningful frame rate difference in any title running today. Those extra cores are completely invisible to games. For everything else, the ceiling disappears. 3D rendering in Blender or V-Ray cuts times dramatically compared to 8-core setups. Compiling large codebases takes seconds. Running virtual machines alongside your primary workload becomes invisible overhead. Complex audio production with hundreds of plugin tracks runs without a hiccup. This is the tier for people whose PC is a work tool, not just a gaming device. Content creators doing professional client work, architects rendering BIM projects, developers running multi-environment builds, all of them will use those 16 cores daily and feel the difference constantly. Spending this much purely to game faster is a mistake. Spending it because your work demands it is simple math. 32 core. Chips like the Ryzen Threadripper 9975WX and Threadripper 7970X exist in a completely different category from everything above. This is not a gaming processor. Nobody should buy it for gaming. Pair a 32-core Threadripper with any gaming GPU and your frame rates will be identical to what an 8-core chip delivers. Games do not know what to do with the extra 24 cores, and they don't try. What 32 cores actually does is collapse timelines in professional environments. Architecture studios cut complex BIM rendering from days to hours. Video production companies process multiple 8K streams simultaneously and stop waiting on exports. Software teams compiling large enterprise codebases go from minutes to seconds. The platform itself is designed differently. More memory channels, more PCIe lanes, larger RAM capacity support. These are not gaming rigs with extra cores attached. They are workstation machines with a completely different infrastructure built around them. In the right environment, a 32-core Threadripper system pays for itself in billable hours. Render time is money. If you're not already listing the specific workflows that would eat these cores alive, this tier isn't for you. 64 plus core. Processors like the AMD EPYC 9554 with 64 Zen 4 cores or the Threadripper Pro 9095WX with 96 cores exist in a world where desktop gaming and most professional creative work stop being useful comparisons. These are data center processors and enterprise workstation chips, running hundreds of virtual machines on a single socket, training large AI models on local hardware, managing rendering farms for Hollywood VFX pipelines, operating cloud infrastructure where downtime costs thousands of dollars per hour. The EPYC 9554 ships with 12-channel DDR5 memory, 128 PCIe 5.0 lanes, and error-correcting memory designed to run continuously for years without failure. It doesn't boost to 5 GHz. It doesn't need to. It runs 128 threads simultaneously with a stability profile no desktop chip approaches. For gaming, your games won't run better, your frame rates won't improve, your load times won't change. These processors cost several thousand to tens of thousands of dollars, and in enterprise environments where compute throughput translates directly to revenue, every dollar earns back. If you're curious about whether you need 64 plus cores, you don't. And if you don't already know exactly what you'd put all 64 cores to work doing, you definitely don't.